What's up guys, I'm back with a new tutorial, and in today's video we're gonna do a concrete impact problem. So the concrete will be reinforced and it will be hit by a wrecking ball. So let's not waste any time and start modeling. So the concrete slab will be having the dimension of 9, 1.5 and 30. So we go to mesh, shape measure, and the box. Here let's say it's minus 4.5, 4.5, so it's total 9. Here is minus 0.75, 0.75, so the total will add up to 1.5, and in the z direction will be minus 15 and 15. And the mesh control, let's say we control by the mesh size, and it's 0.375. Here also 0.375, 0.375, and here I would say this is concrete slab. So here is our concrete slab. Now I'm going to make the reinforcement. Okay, there are several ways to make the reinforcement. We're going to use, of course, a beam element. The first way to make it is straight beam by edge. So here I propagate, then I click this one, and then let me rotate a bit, and here this one and this one, and the last line is this one. Okay, now I click on create and then accept. I hit F2. Now I can see this is the beam elements. Okay, now because of the way that I created the beam elements, they are already attached to the concrete slab, which I don't want. So what can I do is hide this one and then go to translate and then move and make copy. Move in the Y direction, make a copy, and then the direction will be, let's say, 0.75. Trade by part. Select by part, translate. Now I have this. Then accept. Okay. Now I delete the lower part or the lower beams because they are already attached to the concrete slab and they are not in the right position. I don't need them, so I just delete them. Element edit, delete by area, and delete these elements, these beam elements. Okay, now F2. Now you have the concrete slab and you have the beam elements inside. Okay, now we want to create the ball that will hit the concrete slab. Go to mesh, shape measure, and then sphere solid. Okay, let's say the radius of this is 3 and the density is 20. Okay, the position, of course, it will be overlapping, but we can move, we can translate it later. Here this one is wrecking ball. Okay, then create. Okay, now accept. Okay, as I said, it will be overlapping, but it's okay. I can translate it. Element tools, translate by part, and make it 1. Sorry, we need to unclick on this. Okay, now I make it more closer, almost touching. That's the place where I want it to be. Okay, so now since I want this to be a wrecking ball, I want to drop it free fall from a certain height and attach a beam or a cable to it. So let's say I want to create a cable or a beam element. Here I create beam element by node drag, and then I would say this one is 15. In segment, only one segment should be enough. Okay. The front view, click on this element, then you create, sorry, I need to select the direction. The direction is in negative X, and here I have the beam. Accept. Now the beam is already attached or is already connected to this ball. Now I want to rotate this ball so it will be falling from certain height or a certain angle. Element tools, translate by part, this guy and this guy, sorry, not translate, rotate the ball and the beam, the cable that holds the ball, and the origin of rotation is this node. The rotation axis is Z, and let's say it's just 90 degrees. Not this side, the other side. Yeah, is here. So we're gonna apply the gravity and let it free fall while it's fixed in this node, and then accept. Alright, so let's go next and apply the section, or let's first fix what need to be fixed. So I'll go to boundary SPC. This node will be fixed. Create. It can rotate, but it can rotate, but it cannot translate. Okay, so this is the one, and then accept. Now the side, I want it to be fixed, the side of the slab. This one I will fix the rotation as well. Click by select node by area, this one, and then this one, then apply. Okay, so you can see here everything is fixed. Okay, now next is to apply or define the material. I want to define the material of the concrete. So the first material that I'm going to use today is material 159, CSCM concrete. Then new ID, then I will say this is concrete. Okay, now I know you guys are gonna hate me for this, but today I'm gonna use imperial system. So this one will be 2.246 E minus 4. This is 1, this is 0. This is the erosion, to define the erosion, 1.1. This FPC is 1873. Aggregate size is 0.125, and the units will be 3. Okay, because we are using this units which people don't use. Then accept. Okay, this is for the concrete slab. Now we need to define the material of the reinforcement steel. I go to 0.003. This is for the steel. Let's say rebar, reinforcement bars, and the density of the steel in the imperial system will be 7.3 E minus 4, Young modulus 2.9, E to the 7th, Poisson's ratio 0.3, the usual, and sigma yield 3.9, e to the fourth. Okay, strain rate, no need, and failure, no need to define. If you want to define, you can, but no need to define it. Accept. Okay, now I want to define a rigid ball, a rigid material for the ball. Okay, so here, material number 20, then new, and then here, rigid steel. Okay, density is the same, which is 7.3 e minus 4, 2.9, or you can just put 3 e to the 7th, 0.3. And we don't want to fix this rigid material. Okay, accept, because we are already fixing this point. Okay, now define the section solid, new solid section. This will be for the concrete slab and the rigid wall. And then we need to define beam section, new rebar. We're gonna use this one for the reinforcement and for this cable as well, because actually we're not interested in this cable, so we can just put any cross section for it. This one will be, let's say, 0.5, and here is 0.5. CST is cross section type. This is one which is tubular, so it's a tube or a circular cross section with the diameter of 0.5, in our case 0.5 inch. Inside diameter we don't have, it's not hollow, so we just leave it blank, then accept. Okay, we go to part, we assign everything. This is solid, this is the concrete, accept. Number 2 is a reinforcement bars. Beam, it's a beam elements, and the material is the plastic kinematic. The wrecking ball is solid, the material is rigid steel, except, and here, let's say this is a cable. It's a beam elements and it's made of steel, and then accept. This cable is made only of one element, so whether we assign a rigid material or a deformable material, the difference will not be very much in the running time. Okay, so now just to be safe, I control S, I save it, mat 159, and then save. I save it just in case the software hangs in the middle of the way. So now I go to element tools, measure the mass by part here, and as you can see, this is the mass of the wrecking ball. Okay, why I'm showing this? Because I'm gonna show you a trick how to make this solid ball as shell while maintaining the mass. Okay, I will make a new wrecking ball just to compare. Translate in Z, and distance is 0, let's say 0.5 by part. Click on this one. Make sure you copy element. Let's say you copy element. Yeah, you move here. Okay. So now this one I want to make it a hollow ball, meaning I want to delete the inside element of this solid ball. So how to do that? Go to element edit, select delete by part, and then by element propagate, increase the propagation, and then right click on the surface. Now the inside element are still selected. Okay, then by area I want to remove the selection from the new ball as well. Now delete, then accept. Now if you go to blank and you blank by area, you can see that our ball now become a shell, but it's still made of solid element. While this is the original you can see we have elements inside. Okay, unblank both. Okay, now I go to move copy. Let's say this one I want to make it number 10 and select by element, apply. Okay, done. This is just to show you how to maintain the mass of these two. This is a fully solid ball, while this one has only the outside elements. Okay, go to model. Here, this one is a rigid steel. Set. Okay, the way how to do that is either you make a mass element or you increase the density. So what I'm going to do now is increase the density. You measure the density of this hollow solid ball, then you know the target density because you measured the density of this one before. Then you multiply that factor with the density of the rigid ball. So now you go to rigid. You have the rigid steel, right? Make a new ID. Now here you have the increased density. Here you put 0.0078385. How did I get this value? You divide the mass of the solid ball by the mass of the hollow ball. You get this number. This number should be the factor that you multiply your density with. So I did that calculation and I get this value. So this will be the new density. And then I go to part. I assign the material with the new density. Then accept. Okay, if I go to element tools, measure mass by part, you see the part of the mass of this part is this one, and the mass of this part is this one. Okay, I double click here so you can see this one and this one. There is a slight difference in the mass because this rigid ball has the beam element, has one node of the beam element, and that node of the beam element has some mass. That's why the mass of this ball is slightly higher than this one. Okay, so we don't need this guy anymore. We can just delete it. Go to keyword by part and then delete. The material also, this one I don't need it, I delete it. And then this one I just, because I like things to be sorted out, I make it 3. So now we define the contact, which is very normal. This is a standard contact, automatic, surface to surface, new. And then I say wrecking ball to concrete. This is part, and this is part, the slave is part, and it is the wrecking ball. The master is the concrete slab. Accept. Now I want to define the interaction between the concrete slab and the reinforcement bars. That's done from here, constraint. You can use beam in solid, but you can also use constraint Lagrange in solid. Okay, new ID, and here I would say beam and concrete slab. The slave is a part and the master also is part. Okay, Lagrange in solid, The Lagrange's beam and the solid is our solid slab. So the master is the solid and the slave is the reinforcement bars. Okay, C type is the default and direction also is the default. These are the things you don't actually need it. You can just leave it as it is. These are important when you are using ALE, but now we are just using beams and solid, so we don't need to worry much about this. The second, the third, and the fourth and the fifth line. Accept. Done. Okay, now we want to define the gravity. Click on all, then we define the gravity curve first. So we go to define curve, new ID, and here is gravity. Okay, so the gravity in imperial units is 386. Insert 1 times 10 is also 386. Insert and then accept. I did not calculate this one, actually I just took from this page. So here I'm using the imperial units and it's written here 386. So I don't know whether it's right or wrong. I haven't checked it yet. So accept, done. Then go to model, then load body X. See the loads in the X direction. And then here I put this one, and this is a bit confusing, but I need to put minus here. The way that this load body X, Y, and Z works, it will automatically work in the negative direction, meaning if Z is going up, then you just put load body Z and you don't need to put this one as minus. But in my case, everything is upside down actually. Sorry for that. That's why I put negative, because I want it to go up actually. So let's say if this ball was actually up here, then I don't need to put negative here. Okay, but actually I can just do that easily because I can just translate everything, right? So I just put 1 here and then I move this up. Okay, first I want to know what is the location of this point. Okay, it's minus 18. So now I go to element tools, translate, no need to copy, translate in X, and I click by part. Okay, top view. Okay, now go one time it will be in the center and another time it will be up. Okay, this is actually one of the good reasons why you should always practice to make your model in the center, because this one is, because I made everything in the center, that's why it was easy for me to move from down to up. Okay, so let's double check. Okay, it's okay, good. Now we want to define another thing, which is the time interval of the plot. Okay, it will take some time for this guy to reach and hit the concrete slab. So I don't want to waste my memory for that. So I go to curve, I add new, then I would say plot interval. Now the plot will start very rough, 0.01 seconds, insert, and when it is 3.9, the same, and then I change this one, make it smaller, insert, and let's say this is a big number, 10 seconds. I'll just put it, let's say 1 second, insert, accept, then plot. So the plot intervals will be this value until time reach here, then it will change. So at 0.4 it will change. It will become smaller. Okay. Then go to all the database D3 plot. So instead of putting a number here, I just put the curve. Okay, now what left is very important thing. because if we just run the simulation like this, it will take very long time. So I want to shortcut and make the thing faster, because the time that this ball is falling before it hits the concrete, there is no deformation in the concrete. So I might as well consider it as rigid. So I will use deformable to rigid. So deformable to rigid automatic. So new, I'll just make it 1. This code, make it 0. The deformable to rigid will start from 0, and then here I can make it 1e minus 4. Okay, this is, I control the time step and I make it faster. Then here I insert the concrete slab, I make it rigid, insert, and the reinforcement bars, I make it rigid as well, insert, then accept. Okay, I can also insert the cable and make it rigid, but I will not do that because of two reasons. The first one, because the cable is only made from one beam element, so that will not make any much difference in the running time. The second reason, because I'm fixing the cable at one end, and if I make it rigid, it will be more complicated to fix a rigid body at one end. Okay, so only two parts, then accept. Now I make new, or I just add. This time I click here, I put 2, enter, then click here, the same two parts. Now I want to change them back from being rigid to being deformable, and then accept. This I can make it 2. Okay, and here this is the important thing, I make it 0.4. I run this one before, and at 0.4 the ball will almost hit the concrete. So this is the time for us to switch the concrete slab from being rigid back to being deformable as it is in the original file. So to recap this keyword here, at times equal to 0 until infinity, I will make the concrete slab, or I will change the concrete slab and the reinforcement to become a rigid part, and when time becomes 0.4, I change them back to being deformable. Except, so before we run, we got one more thing to do, which is termination time. So control termination, and here I would say, let's say 0.43. Then accept. This time is in seconds. Then control save. I open this. This is a file. You see it's quite fast. Now it's the second switch. It's switching back to deformable. Now you can see the time step drops because you have deformable parts, and of course that requires a smaller time step. Okay, let's see how long it will take. I'll say Control C, SW2. Okay, it'll take 2 more minutes, but I would like to peek on the results and see if things are okay or not. So it's falling. Okay, things are going well. Looks fine. Yeah. We can wait until this finish. It's until 4.3 E minus 1. You can see here we have some failure of the elements. So finally it finished. It took 8 minutes. So let's see the results now. So you can see while the ball is falling, the time intervals is quite big, but when it's reaching and hitting the concrete wall, it becomes small. Alright, So there are few things I want to show you. Okay, you can see here one element have failure, but at the end you have more elements actually from the back. The crack is more from the back, from behind. Okay, now if we click on this and see only the reinforcement, you can see there is a deformation in the reinforcement, which means the constrained Lagrangian solid works because we did not define any contact between the ball and the reinforcement directly. We define the contact between the ball and the concrete slab, and then we define the coupling. We call it coupling using constrained Lagrangian solid. Okay, if we want to plot the results, let's say this is the stress, this is the pressure, this is the von Mises stress. But when I click on this one, you might see it's quite different than what you usually see. When we use this material model, the output, the seventh output, you see 1, 2, 3, 4, 5, 6. This 7 is not actually the plastic strain. This one refers to the damage happens in the concrete. 0 meaning no damage and 1 meaning a full damage. What is the damage model? I don't want to get too much into the theory, but you can read the theory manual if you are interested. So this is our simulation for today. So now I'm gonna modify this file a bit and do another simulation. It will be quite fast, so don't worry. So first I go to history and then go to part, then go to rigid body velocity and click on this and then plot. So now this is the maximum velocity, so which is 11667. I need to know this number. Why? Because in our next simulation, I don't want to make the ball falling because I already know the final velocity. And there is a second reason which I will tell you in a second. So here I copy and then mat 84. So now we're gonna do concrete using this material 84. And this material unfortunately is not supported using deformable to rigid. That's why I want to apply initial velocity, and if you want to carry out this simulation without deformable to rigid, it will take a very long time. You can test by yourself. So here I go to element tools, translate, and then rotate around Z, and then pick origin. This is my origin, then by part this one, and then 90 degree, then positive because we follow the right hand rule. Set, and then go to model. What I do not need is deformable to rigid, and then the gravity I don't need it anymore because I will apply the velocity directly, and then by part, and this cable also I don't need. Now go to all and then initial velocity generation. It will be in the negative y, and our ball is part, so it's 2, then part number 3, and then negative this number, then accept. Done. No need for all the falling drama and all that things. Now since we do that, the binary degree plot, no need for the curve. I just put it 1 millisecond. Now come to the important part, which is defining the material. Click on all. It's material AP4, which is Wenref concrete. New ID, concrete. The density is 2.246 E minus 4. This is the tangent modulus. 4.2 E to the 6th. Positions ratio 0.18. It's very small. The compressive strength is 1873. Of course, this is all in imperial units. Bear in mind, This is 290. Now Fe is 2e minus 4. Aggregate size is 1.25. This rate, I put it number 1. The conversion for the mass is -1. Okay, -1. Conversion for the length is 0.0254, and conversion for the time is 1 because we are using seconds. Accept. Now model part and assign this guy. Concrete slab. Material number 4, Winfrith concrete. Accept. Now I have one more small thing. Database. Binary D3 crack. And then put 0.001. And done. Then don't forget to change the termination time. Okay. The 0.4 milliseconds was actually for the ball to fall, but we don't have the falling part of the simulation anyway, so we don't need that 0.4. So 0.03 will be sufficient. Accept. Done. Then save. Then we run the simulation. This is the file. Now the important part here, the very important part is to type Q equal D3 crack. Okay, if you don't print this one, the D3 crack files will not be printed out. And what are the D3 crack files? We will see when we finish running the simulation. Okay, finally the simulation is done. Now we want to see the results. To make things a bit slower. Okay, we can see there is deformation in the reinforcement bars, so the coupling works. Now, why I choose this material model? First, this material model doesn't have the erosion option like the material that we used before. So if you want to define the erosion, you might want to use add erosion. But this material model has something which other materials doesn't have. You go to open and then others crack file, and this is the D3 crack files that we were talking about. You opened, now you can see actually the crack in the concrete. I want to hide the mesh, and you can see here is the crack. This is from front and this is a crack from behind. We have horizontal, we have vertical, horizontal, and then we have also in the diagonal direction. Okay, so I would say this one is actually much better representation of the crack than the element erosion in this case. Okay, because here you can see you can see only the horizontal. Okay, you can see only the horizontal. The vertical and the diagonal you can see actually from the damage. Okay, this is the damage as we agreed. Using material 159, the effective plastic strain actually represent the damage. You can see we have a damage in the like an X, and also in the vertical and also in horizontal. But here in this one, you can visually see it. Okay. With the fringe component, in this case, this one is actually the plastic strain. It's not the damage like in material 159. Okay, in material 84, this effective plastic strain means effective plastic strain like any other material. So this is, let me put it here, and this one put it here. Let me hide this one as well. So on the left is using material 159, and on the right is using material 84. So that's all for today. Thank you very much for watching. If you learned something in this video, please hit the like button and share the video. And if you haven't done it already, please subscribe to my channel. See you next time.